Let us now look at two important equivalence relations which are referred to as De Morgan's laws, and for that we will use the truth table to establish those equivalences. The first of the De Morgan laws states that the negation of the conjunction of P and Q is equivalent to not P or not Q. So, I have here not P and Q, and for every legal values possible for P Q, I have here not P or not Q. As the truth values of these two propositional logic formula are the same, so these two formulas are equivalent, and I could write that the negation of P and Q is equivalent to not P or not Q. Similarly, we have the second De Morgan's law which says the negation of the disjunction, that is not of P or Q, is equivalent to not of P and not of Q. And I will leave it as an exercise for the readers to figure this out, that these two propositional logic formulas are equivalent. Now, these two formulas, the not of P and Q as not P or not Q, have the same truth values as we saw. We say that they are equivalent to one another. Let us now focus a little on what we mean by the equivalence relation. The symbol of equivalence that I have used here is not a connective. It is related to the biconditional, but one needs to be clear that it is not the same. The statement that not of P and Q is equivalent to not P or not Q means that the two formulas are equivalent. Whereas, if I put the biconditional there, then the statement is a propositional formula, and if you plug in different values of P and Q, it will evaluate to a truth value. Interestingly, the formula evaluates to true every time. One more useful equivalence is the following: P implies Q, or if P then Q is equivalent to not P or Q. Let us try to establish that by starting from the implication. So, we start with the implication, and by definition, if we look at the truth table of implication, we see that implication is equivalent to not of P and not Q. We thereafter can use the De Morgan's law to expand this out to its equivalent form, which is not of P and some W is same as not of P or not of that W, and that leads us to this being not of P or Q. Does P implies Q is equivalent to not P or Q. This is a very useful equivalence that we will be using when we will be working through the proofs, both in propositional logic as well as in first order logic. Let us now focus on what we mean by rules of inference. A rule of inference is sound if its conclusion is true whenever the premise is true. So, here are some examples of sound rules of inference, and each can be shown to be sound using a truth table. The first one, modus ponens, is like I have A implies B, and I know A, Therefore, I could conclude B. A implies B, A, therefore, I could draw the conclusion B. The next is about AND introduction, which is in the premise if I know both A is true, B is true, then I can conclude A and B. The third of the rules of inference is the AND elimination. So, if we have the conjunction A and B, then we know that this statement is true if both of them are true. Therefore, we could write A, or equivalently we could write B. So, A elimination is A and B leading to the conclusion A. We have double negation, which we have used little while ago in the previous slide. The negation of A is A itself. We have unit resolution, which is A or B and not B is A. And finally, we have a very important rule of inference, the resolution, which is A or B, not B or C, leading to A or C. So, these rules of inference that I have, I will come back to this when we will discuss proofs in first order logic in more detail. So, a proof is a sequence of sentences where each sentence is either a premise or a sentence derived from earlier sentences in the proof by one of the rules of inference. The last statement that I arrive at in a proof is referred to as the theorem, or also called the goal or the query that we wanted to prove. So, here is a small example from the weather that we are talking of. So, Q represents that it is humid. If Q then P is the statement that if it is humid, it is hot. From 1 and 2, I could use Modas Ponens to arrive at that it is hot. Q implies P, Q therefore P. So, I can say it is hot. Next, if I am told that if it is hot and humid, it is raining. So, that is the premise that I know. Now, given this scenario, I can use 3 here and 1 here to do an AND introduction and get to P and Q. So, I know it is hot and humid. Given 4 and 5, I can now conclude that it is raining. So, here in this example, I have the propositional formulas in red as my premise and in black the sentences that has been derived either from earlier sentences or from the premise itself. And finally, I could have a theorem that it is raining. So, we have looked at propositional logic and we have seen that it has logical constants, propositional symbols, we have parentheses. Sentences are combined by propositional connectives of conjunction, disjunction, implication, biconditional and negation. Propositional logic commits only to the existence of facts. That may not be the case in the world being represented. It has a simple syntax and very simple semantics. Propositional logic is sufficient to illustrate the process of inference, as I have done in that weather example. However, propositional logic quickly becomes impractical even for very small worlds. Let us see what we mean by that. So, consider the problem of representing the following information. Every person is mortal Socrates is a person, Socrates is mortal. How can these sentences be represented so that we can infer the third sentence, that's Socrates is mortal, from the first two? In order to do that in propositional logic, I would need to create propositional symbols. So here I have P to mean that he is a person, M, he is mortal, and S to represent Socrates. The first statement, every person is mortal, roughly could translate into if P then M. This is exactly not the statement that every person is mortal. What this statement is saying is, if somebody is a person, then he is mortal. The next one, Socrates is a person, could be written as S then P, and from the first two I could derive S is mortal. Now, although the third sentence is entailed by the first two, an explicit symbol to represent the individual Socrates was required. What that means is that if I have to now represent other individuals, I would need to introduce other explicit symbols. And this I have to do for each of the person that I want to talk of. And then I must also have some way to represent the fact that all individuals who are actually people are also mortal. So propositional logic is a weak language. It's hard to identify individuals, so we cannot talk of things like Mary or the number 3. We can't talk of properties of individuals directly or even relationships between them. Like, all I can say in propositional logic about Ben being fat is to have a proposition P to say Ben is fat. Generalization, patterns, regularities cannot easily be represented. It would be really difficult to write all triangles have 3 sides in propositional logic. First order logic, on the other hand, is expressive enough to concisely represent the kind of information that we are looking for. First order logic allows us to get to the internal structure of certain propositions in a way that is not possible with propositional logic. First order logic adds relations, variables, and quantifiers. So we could talk of things like every elephant is gray, or we could say there is a white alligator. This is what we will look at in our next lecture. We will first introduce first order logic and then look at proofs within first order logic. Thank you.